Hello friends, I welcome you in lecture number 14 on partial ordering. In this lecture we are going to discuss about lattice. A lattice is a special type of partial ordered set. If a partially ordered set satisfying certain conditions, then it is called a lattice. So we are going to understand the definition of lattice together with one question asked on lattice in GTU exam in this lecture or session. So first we understand what is lattice. So we have discussed about least upper bound and greatest lower bound of a subset of a partially ordered set in lecture number 13 on partial ordering. We require these two definitions to understand the definition of lattice. So if you have not seen earlier lecture, which is lecture number 13 on partial ordering, then I suggest you to watch that lecture first and then go for this lecture. In fact, we require all the terminology related to partial ordering which we have discussed in this playlist on partial ordering to understand these lattices. So I hope you are familiar with all the previous lectures terminology, and now we are going to discuss lattices. So suppose I have some partially ordered set, say capital P, with some partial order relation, and we can denote it by these different notations. So P is a partially ordered set, that is shortly poset. Now when this poset becomes lattice, or when we can say that a partially ordered set is a lattice, so we have one condition, that if I take any subset which is having two elements of given poset, if I take any two elements in a set P, and if I construct this subset having these two elements, and if this subset has least upper bound as well as greatest lower bound in a poset P, then this poset P is a lattice. So we can say that a partially ordered set P is called a lattice if for every pair of elements, AB in P, this subset has a least upper bound as well as greatest lower bound in a poset P, and the least upper bound of this subset is denoted by A star B, greatest lower bound is denoted by this symbol. There are different symbols for this least upper bound as well as greatest lower bound. This is one symbol. Another symbol is A meet B, or A and B, or A dot B, or simply AB. Similarly, greatest lower bound is also denoted by A or B, or A join B, or A plus B. So remember all these different notations also for LUB and GLB of this subset of a partially ordered set P. So with this in mind, we consider one question which was asked in GTU exam. Before that, they can ask you to define lattice, so you should write systematically that a partially ordered set, we will denote lattice by capital L, therefore I have written capital L here. A partially ordered set L in which every pair of elements AB has both a least upper bound and a greatest lower bound is called a lattice. So to check whether given poset is a lattice or not, you have to check for every pair of elements that whether for every pair of elements this subset AB has a least upper bound or not, has a least upper bound as well as greatest lower bound or not. If we can find out at least one pair which is not having either least upper bound or greatest lower bound, then our set is not a lattice. So here I have taken this example or question which was asked in GTU Summer 2020 exam. You can see they have asked the definition of lattice. So you should write systematically what is the definition of lattice. and determine whether the partially ordered set having 5 natural numbers with divisibility relation is a lattice or not. So we can denote this set by some notation. Suppose we use capital P. Here we have 1, 2, 3, 4 and 5, and we have to check whether this P with divisibility relation is a lattice or not. Now I have to check for each and every possible pair, or I have to write that possible pair which is not having least upper bound or greatest lower bound. So we can see that there are many possible pairs. So we can start with 1. We fix A equal to 1 and we vary second value of B. So possible subsets are 1, 2, 1, 3, 1, 4, 1, 5. Then we can fix 2 as value of A, then we can vary B as 3, 4, 5. So in this way we can check whether every pair of elements has a least upper bound or greatest lower bound. Suppose I check for this pair, set having 1 and 2, then I have to decide whether it is having least upper bound and greatest lower bound. Now we are familiar with the definition of upper bound. So here we can observe that 1 divides 2 and 2 also divides 2. This means 1 and 2 are related to 2. Therefore 2 is an upper bound of this set having two elements 1 and 2. Similarly, we can say that if we take 4, then 1 divides 4 and 2 divides 4. Therefore 4 is also an upper bound of this subset, and therefore there are two upper bounds. There is no other element of P which is candidate for upper bound. So we can see these 2 and 4 are upper bounds of this subset, and 2 is the smallest one, so that is our least upper bound. So I have obtained least upper bound of this subset having two elements 1 and 2 as 2. Similarly, I have to decide the lower bounds and then greatest lower bound. So greatest lower bound is greatest element out of all those lower bounds. Now for lower bound we have to decide that element of P which is related to every element of this set. So it is obvious that if we take 1, then 1 divides 1 as well as 1 divides 2. This means 1 is the lower bound of this subset having two elements 1 and 2, and there is no other element which is lower bound of this set. So there is only one lower bound, and therefore it is the greatest lower bound. Greatest lower bound of this set is 1. In this way I have to decide LUB and GLB, or I have to find out least upper bound and greatest lower bound for each possible pair. I have to check for every possible pair that whether LUB and GLB exist or not. So now I can check for 1 and 3. So now if I write directly that if I consider 1 and 3, then what are the upper bounds of this subset 1 and 3. So here we can see 1 divides 1 and 3 also divides 3. 1 divides 3 and 3 divides 3. Therefore 3 is a upper bound of this set, and there is no upper bound except 3. So least upper bound will be 3, and you can check that greatest lower bound is 1 because 1 divides 1 as well as 1 divides 3. So greatest lower bound and least upper bound for this pair also exist. Then if you check for 1 and 4, then also you will have 4 here and here 1. Least upper bound of this set 1, 4 is 4, and greatest lower bound is 1. Similarly, if you check for 1 and 5, then you will find that least upper bound is 5 and greatest lower bound is 1. Now I fix my first value as 2, I have checked for all the possible pairs in which we have first element as 1 and we obtain least upper bound and greatest lower bound for all possible pairs. Now we fix our first element as 2 and we vary second elements as 3, 4 and 5. So first we check for this subset 2 and 3. Now I have to decide that element from P such that 2 divides that element as well as 3 divides that element. Whether there exists any element in a given set P such that 2 divides that element as well as 3 divides that element. And you can see that there is no element here which is divisible by 2 as well as 3. What is meaning of this? This means this set has no upper bound in a given partially ordered set P under divisibility relation. There are no elements in capital P which are divisible by 2 as well as 3, or there is no x in P such that 2 is related to x as well as 3 is related to x. Therefore, this subset has no upper bound in a given partially ordered set P, and if we have no upper bound, then certainly we don't have any least upper bound. So least upper bound does not exist for this subset having two elements 2 and 3, and therefore this partially ordered set is not a lattice. If it is a lattice, then every pair of elements must have LUB and GLB in a given set. So if your partially ordered set is not a lattice, then you have to write down for that pair only which is not having upper bound or lower bound in a given poset. So we can write that the subset 2, 3 is a subset of 1, 2, 3, 4, 5. Okay, 2, 3 is a subset of this, and 2, 3 has no upper bound, and hence no least upper bound. 2, 3 has no upper bound and hence no least upper bound in a given partially ordered set having 1, 2, 3, 4, 5 with divisibility relation. Therefore, this partially ordered set 1, 2, 3, 4, 5 with divisibility relation is not a lattice. So in this way we can check whether given partially ordered set is a lattice or not. All we have to remember is if we take any pair of elements AB, then this subset must have least upper bound as well as greatest lower bound in a given partially ordered set P. And if you want to prove that your set is not a lattice, then you have to find out at least one pair which has either no least upper bound or it has no greatest lower bound in a given poset. So we will continue with lattices in upcoming lectures, and I hope you are able to understand what are lattices now, and if you have any doubts you can ask in comment section. Thanks for watching.